Photoshop, we wanted to have a kind of clean, simplistic look that also attenuated flight, which can be seen on these little envelopes around the sides. So our project overview, we wanted to design and create a functional operator.
We wanted to have autonomous or mission-based path for the flights.
And most importantly, we wanted it adaptable to a variety of environments and scenarios.
So our individual project objectives, I was responsible for the mechanical aspect of the project. First was I wanted to optimize flight performance, and that included flight time. I wanted to research manufacturing techniques and common materials. With that, I wanted to earn the CSWP. I also wanted to learn Eagle, which is a free PCB design software, and also wanted to investigate modularization within the project.
Alright, so some of my objectives for the integrated control were to actually design and build the actual quad-auto control system. I wanted to create some form of spatial awareness using sensors. I wanted to design a system for flight diagnostics, and I also needed a way to stabilize the quad midair, so I needed to investigate and create stabilization loops, as well as manage an Android connection to the Android stack.
So for the Android objectives, I worked on the Bluetooth connection, sending data back and forth between multiple devices. Three-dimensional control system, so how do we tell the pod where to be in 3D space? A dynamic mission control, which is different ways we can control it, and fully publish and release an API of the source code so other developers can work with it using.
So moving into the timeline, this is what really guided us throughout the year as far as organization. So in the early process, I researched all the components that we would be using in the final design. I also created an initial testing design that we created early on in the year, and also a lot of the front-end work, such as this timeline, product proposal. Moving into November, I constructed the initial testing chassis, and also started doing the research with the Eagle PCB design software. In December, moving up towards winter break, I completed the initial testing chassis, did all electrical connections between the different components and microcontrollers that we have, and we also completed our job shot at locking them. In January is where I did a lot of research into different UAV examples, both multi-rotors, helicopters, and planes, to see different manufacturing techniques and materials that people were using at both the hobbyist and professional level. In February, I used a lot of the things that I learned from that and implemented them into the final design, which you can see here. And that's where I started doing a lot of brainstorms, a lot of sketching. I also earned my CSWP in February, and I also learned how to do static simulations in SolidWorks to test the structural integrity of the parts I was creating. And then last month and this month, March and April, finished the construction of the final design, did some animations to get a nice presentation going, and also did the documentation, which included binders, boards, website, and this presentation.
Okay, so a bit on my integrated, so a bit on my integrated control timeline. So in October, I just basically learned all about the electronics, which include the flight board, which does all the stabilization, and I also began my initial design. I created a boot sequence which integrated and connected all the electronics, and I researched what main processor I wanted to use. I was on the fence between 4 possible computer systems for the entire fleet. Also, in December, I created a theoretical thrust curve system, and as well as I researched PID methods, which are ways of stabilizing midair. In January, I finished my prototype of the control system, which we'll have some videos of later, and we created the serial comm interface to the Android device. In February, I actually switched all my code over, which was about 1,000 lines of C and Python code, into Simulink, and I taught myself Simulink, which is a space or control system which I use in spacecraft and other engineering applications. In March and April, I tweaked my Simulink program to be able to do diagnostics in there, so we can have live graphs of data running across the quad system. And I also did the presentation.
So for my part of the project, starting in October, I started learning the basics of Android, which consists of Java and XML, 2 different programming languages. I started testing Bluetooth in November and different test applications. And then going on to December, I did universal communication, so how can we get different devices to connect to each other, and how can we send data back and forth. Moving on to January, I worked on activities, fragments, and menu system. So that's kind of the way we build Android activities. So I'll talk about that a little bit later. In February, we have the mission control and the timer system. And then moving on to March and April, we finished up all the code and put together a final presentation.
So we'd just like to talk about some of the key research that we did throughout the project. The first part was the components that goes into that. The motors, the batteries that we wanted to use. This stems a lot from RC components, like I said earlier. So the first is the motor. This is the AX2810Q 750 kV. It was a popular motor that I saw in a lot of different builds that I was looking into. The next are the propellers. The battery, this is a LiPo battery, it's rechargeable, 4-cell, provides a great amount of power for the motors. The electronic speed controllers send signals to the motors to actually produce the thrust for them to control them. And then the flight controller was something that was very key to our project. In a normal RC application, it receives input from RC transmitter receiver pair, and then outputs that to the electronic speed controllers, which then output thrust to the motors. What we had to do was replicate what an RC receiver would be sending with the Arduino, which Jason will talk about later. And then also a lot of miscellaneous connections to make everything fit together nicely. And then the next part that I was researching was the electronics. As I said earlier, I learned Eagle, which is a free PCB design software. Used a lot of tutorials by a man named Jeremy Bloom. He is a software architect working on the Google Glass project. We didn't end up having to use that in the project, but it was very useful to learn that knowledge as far as board design, circuit design, and how to actually produce boards. And then the second part of that was power considerations. All the different components require different voltages. For example, the motors need the full voltage of the battery, whereas the more precise microcontrollers need less voltage, usually 5 volts. And so how to think about how to power everything with a single motor and with a single battery. What I spent the majority of my time researching in January was different manufacturing and materials. So one was Garolite, fiberglass and epoxy laminate that comes in sheets. This is very light and very strong and would be something that I plan to develop into the project. These are plastic sheets which are very easy to laser cut, and which we've been able to do in school. 3D printing, this is a very interesting, relatively new manufacturing technique that I was very interested in researching and learning more about throughout the year. It allows rapid prototyping, which essentially means that you can take an idea, create it in SolidWorks, and then with a couple of hours, depending on the size of the part that you want to print, have that there. Use that for the arms, and then a couple miscellaneous mounts that we have. And then the laser, like I said earlier, was used to cut the acrylic sheets. And then CNC milling, which is a subtractive process, which is the opposite of additive process of 3D printing. And then the last was SolidWorks. This really went into earning my CSWB. I wanted to learn a lot of little things that make SolidWorks a lot faster and easier to use. I also learned how to do static stress testing, which I use to test the arms. You can see here, this is an example test of the arms. It shows the displacement. Red is greater displacement under a certain force, and then blue is less. You can see color spectrum through here. And then there's some minor difficulties with 3D printing due to the differences in the SolidWorks model and what is actually produced by the 3D printer. And then the last was learning how to do animations and exploded views. to the greater extent that I had before.
So the big part of my research was into wireless communication. So a lot of people take it for granted that we can just connect different devices without having to plug things in, but it's actually a very hard process that requires a lot of work. So I chose to use the Bluetooth devices that connect to each other. And so Bluetooth, how it works is it creates different sockets, which is an outstream socket and an instream socket. And this works as a way to send data across. Now this is only a one-way connection, so we have to create two sockets on each device. And that's kind of how Bluetooth works in a very simplistic way, how to send bytes across the connection. Another big part of my project was the universal protocol. We had over 6 different coding languages in our project, so it was very hard to tell one device to talk to another. So a big part of my research was how can we send data across different devices that everyone can read. And another thing, so the universal protocol which I developed, I modeled it off of kind of the postal system. So on every package you send, you have a sending address, so where the packet is going, a return address, so where the packet came from. You have the stamps, which tell you how much the package weighs and kind of what's in the package, and then the contents of the package itself. So I modeled it off of this, where you have the send to, the return address, the size of the packet, an identifier of what's in the packet, followed by the content. So these are sent across as strings. So they start with a caret, and so say we send to the Raspberry Pi from the Android, the size of what we're sending, and then the data that we're sending. So these are just kind of examples of how these then get broken down and what actually gets sent across the Bluetooth connection. I also had to do a lot of work on the Android application, writing it and developing it. So it's written in Java with an Android syntax, so there's lots of Android-specific classes for Java. And XML. If anyone here has used HTML, it's just like that for the most part, except it's for a mobile platform. It's really how different things interact and how things are laid out with each other. So it's saying that this object is here in relation to everything. So it's a way to lay out all the different elements on the screen. Activities are how you display objects in Android. So each screen, when you pull up an app, each screen is a new activity. So say you open the app and there's just a button. That would be the first activity. And then when you click the button, it would launch a second activity that might contain text or a picture or whatever the button is supposed to do. So really you can create very dynamic applications with all these different activities and say which launches what and kind of create a flowchart of how things connect to each other. There's also a thing called fragments. So if you don't want to present a full screen of data to a user, you might want to send a little fragment. So fragments can be resized for different purposes. So say on activity A, you want to run a fragment that displays a picture. You don't have to take up the whole screen and display a new picture, but you can launch a fragment. You can run multiple different fragments off of the screen. Also, if you have an activity, and say you have a fragment of text at the bottom, say the user swipes to the side because they want to access more content, you can display another fragment on top of it. So these fragments are ways we can stack things while still staying on the same activity. So we can have a menu system or a title or something up there while scrolling through multiple different content. Navigation drawer is the menu system equivalent in an Android application. And a list view, which is ways we can display lots of data in a scrollable fashion.
All right, so a bit about my onboard control research. So for the most part, I had to mainly research like how to actually communicate between all the electronic devices on board, and how I would do that in both the hardware physically connect them, as well as in the software generate the proper signals to give the proper output. So as you can see here, here's the data we'd be sending from the Arduino, i.e. the decision maker, what we want the quad to actually do. And so we have this board in between them that actually controls the motor speeds on the quad. So I had to learn how to generate this type of signal, which is called PWM, or pulse width modulation, as it transfers information in the size of the actual pulse it sends on the line. As you can see, it ranges from 0 to 100% here as the size of the wave gets bigger. And so I actually had to learn how to, which signals to send and how to actually send it to effectively communicate. I also had to, although I had to teach and work with a lot of programming languages, the project, the most relevant one now is Simulink. And Simulink is a part of MATLAB, and it basically looks just like this. It allows you to program and create robots or any other systems in a very easy flowchart type fashion. This was actually, this is a snapshot of some code I did in my research project for a TSA state competition. And this is actually, so I taught myself the language by actually building another robot with it. Simpler one, this one just follows a line on a track, but still, I had to familiarize myself with the way of transferring data and processing things in these systems. I also had to learn about PID control loops, which is the way to keep, which is the way we use to actually keep the quad stabilized and flying in the air, and hopefully, theoretically, in one spot. And it works off basically the principle of homeostasis. So we have so this is the point where you are now, point A, and if you want to go to point B, you see what's the difference between point A and point B. And basically, what's the error between where you want to be and where you are now. And so, basically, the amount of change, i.e. in the quadcopter, it would be the amount of change from the amount of change in the thrust output, i.e. from point A to point B. We would, it's the bigger the change, the bigger the change in the thrust output, and it also follows with the smaller the change, the smaller the change in the thrust output. And so what that allows for is to not only make for large corrections, but finer adjustments in your stabilization. And so now on to the final.
So we'd just like to touch on some of the major accomplishments that we've made throughout the year. Here's a quick cost breakdown of what it would actually cost to recreate what we have here and continue to fly it. So some of the these are most of the RC components that are actually making fly it. Here we have the processors, battery charger, the sensors, and this miscellaneous cost is things like tax and shipping. And so it comes to about $515. And so the chassis, some of the majority of what I focus on were the 3D printed arms, the laser cut acrylic, and the landing gear. Here's a quick picture of the arms with the ESC and motors mounted on it, and here's a view from the other side. This is where the acrylic sheets fit into. Here's a quick view of the top. Let's see closer afterwards of the actual design. And then this is the weight of the initial testing chassis. It was about 1.6 kilograms. This is about the same weight, but it also includes the landing gear. And here's a quick picture of the landing gear. These are 3D printed adapters, and this is some rod got from Home Depot. It's just easier and quick to use, but it would be very easy to switch it with something lighter and stronger. And then for the electronics, the goal was to make it compact and minimal, to get the sensors on there and to use a single battery. At first, we were thinking that we might have to use 2 different batteries to power the electronics, Arduino, OpenPilot, and then a separate battery for the motor. But in the end, we were able to find a way to power them all together. Here's a quick view of the different sensors. This is the Arduino Mega that we were using, and the 3 ultrasonic rangefinders are mounted around the outside. Then this is the power distribution board that takes power in from the motor and distributes it to the 4 ESCs.
So for the final Android application, I have a bunch of screenshots, and I'll kind of talk about what each screen does. So this is kind of just the opening screen when you launch it, and after you connect to a Bluetooth device, this is what shows up. Opening the menu by clicking up here, you open the menu system, which is a navigation drawer. So we have the attitude control, the flight diagnostics, point-to-point command, and mission control. We also have loss of room for different menus if we want to add them in the future. Here we have the flight diagnostics. So when the quad is actually running and it's connected, we can receive real-time data for all these different data points. So this really helped us troubleshoot it, and when we're trying to test things, we can see how different values react when we do different things. Here's the attitude control, which is just a basic slider. So you can increase the thrust, the roll, the pitch, and the yaw. So it acts as a kind of a rudimentary RC controller, so you have some basic control. Here's the mission control, which was probably the biggest focus of my Android application. When you open it, you just get a blank screen here. But what you can do is go down and hit add a command. And you have an option right now of 3 different commands. We have an attitude control, a pause, and a point-to-point control. So here, I just started a mission and just created a basic point-to-point. So it's going to tell the quad to move to a point, and that point would be a Y value of 1 foot, so it would raise 1 foot off the ground, and I want it to be completed in 10 seconds. So now if I were to say, launch the quad, the Android would then tell the quad what to do over Bluetooth. Here's a more dynamic mission and a larger one, so you can put together lots of different things, like a basic attitude control, adding pauses, and different point-to-points. So this can be really expanded in the future. We can add more types. So you could say, like, search a room, or look for an object within a space, or map an environment. So that's really the majority of what I worked on. And then here's just, if you do a point-to-point control, this is the screen that shows. And it's just, you can enter different values there, and set the duration, and then add the command.
Alright, so I accomplished all my 4 main objectives in the onboard system. So first thing that I did was I created the serial interface to the actual Android device. As you can see here, I have this is my Simulink code as well as a flowchart and an easy way to visualize the process that the program takes. So here, as you see here, we have a serial port open. This is direct line to the Android device. And as it's going through, it's capturing messages from it, and it checks to see if it's a valid message, i.e., whether it was actually Drew who sent it or some other nefarious person. So then we take that message and we process it, and it goes into the command execution matrix. So what the command execution matrix does is it makes a decision on what to do next. And so all these processes have to be calculated down to the millisecond what it's going to be doing at each point. And this is also down to processing each byte or each packet of 1s and 0s. And so into the command execution, we take, each packet comes with an ID from Drew's device, and from that we can make a decision on what to do. So if it was had an ID of the thrust output, we know that Drew is sending a command to say that we need to change the thrust output or the throttle. Or we might have a command to say, like, hold this position, or in the future we can have it so it can be any variety of things. It's very expandable and easy to implement new functionality into it. Part of what I also accomplished was working with this system, and this is an example of us working with. Should be a YouTube. Well, as you can see here, this is the prototype model mounted on one axis, and what it should be doing is, well, actually, you can actually even see in the picture, it's holding an angled position. So we commanded it to hold this position, and what it will do is it will adjust its motor outputs so that it will hold that position no really what would be thrown at it. So like, if there was wind or something, it would actively adjust its output to try to overcome that change. Okay, so this was a video of our first crash, and so basically what we did is we ramped up the throttle on it and just to see what would happen, and we didn't have a tether at the time, which was unwise. But anyway, so we ramped up the throttle, and then it eventually starts to drift because there's it'd be like if you were just slamming on the pedal of your car and you weren't even holding onto the steering wheel. And so that's why we had to move to the PID loop control. And so what the PID loop does is it uses sensors to actively monitor the cloud position of the loop. So we have 3 sensors monitored on each axis, that would be the X, Y, and Z. So it would be facing like a wall over there, like down, and then possibly forward. And so now, if we can control our position on each axis, then theoretically we can hold it still in space. And so the idea is we have a commanded altitude, so what the user would set where the quad needs to be, and we have the current altitude being measured by the sensors. And so we calculate the raw error between the two, and then the percent error, and then we multiply it by a gain value. And so all that means is we can adjust how much it reacts to error. And we also have a derivative of error, or the change in error as it goes over time. And the functionality of that is that it basically works in the same way if you were approaching a stop sign and you notice that your car is already slowing down. So that means you actually don't have to put on the brakes as much. So it keeps in control the program. It makes it a little bit more intuitive and smarter. And so now about our future development.
We plan to continue developing this into the summer and possibly college. So for me, I'd like to switch to more professional materials, for example, the gear line I was talking about earlier, or possibly doing a professional print of the 3D arms at either a college or a business. Then I'd also like to do a material study to see, kind of get some empirical data about how the arms and different parts react to different stresses. And then I'd also like to implement some design features. One of them that I was working on throughout the year was the landing gear. I'd like to make some improvements on that. And also adding the prop guard, possibly a package drop system, which would be able to work very easily with the Arduino that we have currently, and maybe even camera minimal. I think it would be very interesting to get into photography as far as mapping.
My next step in the control system would be to convert it over from MATLAB, which is a closed source, i.e. you have to own a software license to use it and actually market it, to open source, something that we can use for free. I'd also like to be able to get a live camera feed being sent to the Android phone. I believe if we need to actually account for and make changes to the actual design to do outdoor flight, which introduces a whole new host of other variables, and perhaps a return home function. So no matter where you really flew the quad, it would be able to use your GPS location on your phone to actually come back to the user.
And then further development on the Android application would be A-star pathfinding, which is just a type of pathfinding. So the quad would have kind of intelligent flight around a location. Increased missing control, so that's different values, such as like search for something within an environment or map an environment, different things like that. And a custom user interface. If you could tell, I was using the default Android elements, but going through and kind of making a customized interface would be pretty fun and challenging. So this is our bibliography. It's pretty long. We're actually going to show some of the videos that Jason was unable to play. And, well, that's a computer one, so. And so, unfortunately today, we will not be demoing the quadcopter. At this stage of development, it is very crowded in here, and there's too many people, and there's a lot of unknown variables. And once these propellers get spinning very fast, they are very dangerous. So we don't want to hurt anyone. or anything within this room. So unfortunately, we will not be able to show it, but we're going to be pulling up videos shortly of some of our testing.
While we wait, does anyone have any questions? Questions? Anyone?
Here we go.
I mean, if we had a large quad, large mill. As of now, it's probably medium to small.
What kind of progress did you make on the theoretical mapping while moving?
Well,
Resources you
it would be too random and hard to explain if to even include it in the presentation, but we did actually work with a Kinect camera earlier in the year, and we were able to actually get a 3D map of like a room, but it eventually became irrelevant and not important when we were actually just trying to get the system itself to fly, and so we kind of cut it out.
So with only one sensor on your quadcopter, are you planning on adding like, one sensor on the sides?
Right.
of it. So that, would that limit how it works in terms of like getting this location in 3D space?
Well, we could add more as the design process goes along once we have more money. Because we're really kind of limited financially on how many sensors we can put on and the caliber of sensors of what we can do with those.
Okay, so one of the like at altitude adjustment. So like let's say you kind of take up like from the table and then you move it like really high, and then its altitude is something to be decreased.
It would, well, current design, it's not a kind of table, so it would drop in altitude immediately and try to get back to whatever height you set it relative to the table. And maybe in the future, we can have it dynamically adjust for that, but right now it's just design.
How does it do with other conditions?
Well, we've never tested it in weather conditions, but actually this video could give you a sense of it. If you can imagine Connor's hand is like a wrathful hand of a storm. And so like you can see it's being held on one axis, but it still demonstrates the behavior of how the actual algorithms work, and see how it adjusts the speed of the motors to actually stay stable in one spot. And so now we're commanding it to an angle here, and it's still going to adjust it's still going to adjust the speeds to actually keep these pitch and roll values.
It's actually very resistant to the change. Trying to pull it down is actually pretty hard to get any change in the angle.
And so, yeah, this was one of our first flights. So this is one of our first flights, and it demonstrated in a prototype what we actually need to build. And so as you can see here, it takes up and it has enough power to lift itself, but it eventually drifts to the side and crashes into it.
I told him by law of profits.
And so that's what we decided. We needed sensors on the side to actually keep it stable in flight. And so instead of outputting one value to actually keep it stable in space, we're constantly changing that and making new calculations for it. And this is one of our first flights outside. You can see it's more tethered. You'll eventually see later on how the wind will actually cause it to go a little crazy. But that's why we also needed a way to actually anchor it to some objective. And so for the use of the distance sensors, that's a way of virtually anchoring it to either the wall or the ground.
Cool.
And, all right.
So you touched on using a Kinect camera earlier. Would it be possible to use that Kinect camera and have it on there once it and just wait the feed to the phone?
Oh yeah, most likely. I mean, it's that. I mean, anything's doable. It's just within the scope of this project is
How does the cost of your rig compare to commercial ones?
It's
Very,
comfortable.
very good. On the market, there's a very popular hobbyist quadcopter, and it costs around 3 times the price. Now, if we were to actually mark this up for retail, it would be more expensive, but it comes in at about a third of the cost that if you were to buy a professional version. So it's really good for that.
So, talking about the camera, if you put a camera on, would you need to add another battery, or is there enough power in that battery to also power the camera?
There would be enough power. It would just be a matter of stepping down the voltage. One thing is that the ESC is there, what's called the battery elimination circuit, and that gives out 5 volts, which is actually what we figured out we'd be able to use to power microcontrollers. And so the Arduino Uno is the main microcontroller that we're using, and that would be able to supply power to any extra sensors, cameras, things like that.
In terms of, because quadcopter has a lot of thrust and ability to work off, what can, besides itself, how much do you think that it's going to carry or lift up, or have you tested that at all?
Based on the weight that we got and some calculations, it would be about 4 pounds extra.
Okay.
It's about 3 pounds right now.
Yeah, well, so what did you guys find was the most difficult thing? Because I know your plan was pretty big at the beginning of the year. Why all the changes? Just explain some of the things that you've learned.
The most difficult thing was that it's far more different. It's far different than other technology projects. Because for other things and other coding expenditures, you can test like 1,000 times, see if something works. But if we were to test more than 5 or 6 times after the job for test runs, then we could destroy all our equipment, and we don't have the money, the funding over time to keep buying and getting new resources. So we have to be careful and frugal with how we test. And that was, we had to overcome that by actually running more simulations rather than test flights. And so that was, I did that with Simulink, which was able to simulate also on the computer what the end output would be, and cognitively stress testing for that in that regard.
And another part of that is that the way that we're using these RC components and different processors is very different than what most people do. So although there was a lot of information about the parts, it wasn't all necessarily relevant to what we wanted to do. So we had to do all the testing, a lot of teaming to make it all work.
Any other question?
What's battery life like?
It's about 15 minutes, which is pretty common for most quadcopters. That also does depend on how aggressive the flight is. So if it was just hovering, that would be longer than 15 minutes, but in the same wind, that would be cut down.
Any other questions?
Did you create a, well, not create, but like, how did you set up the battery to be able to last longer than 15 minutes?
Better, just, me personally probably didn't do anything, because like that battery there, it's the big yellow brick at the bottom. It's the same material and technology as in your phone, and your phone's like really thin, like its battery, it still packs like has a lot of power. So that has actually a ton of energy, and it's like 15 volts, and if you accidentally connect the leads, we've started fires and small.
Yes, they have.
And so it's, right now it's about at maximum for like weight to like power consumption ratio. That would be optimum.
It would just be about increasing efficiency, making it as light as possible, and also with the advances in micro technology, batteries would become more efficient as well as lighter. So that's something that will come.
Perhaps solar panels.
Good.
What would be the potential application of your technology in the world today?
So there's drones are a very emerging industry right now. There's things such as like agriculture. Farmers can use this to monitor fields of crops. Forestry. There's a lot of like power lines. You can regulate power lines and like fly the quads up and down and look for maintenance instead of having to send someone along the whole lines in like barren places. A lot of surveillance. Delivery, Amazon's kind of looking into that right now. We'll see if that actually pans out. So So there's a decent amount, and a lot regarding like military, like defense and surveillance.
What's very useful about it is that it can get to places that most other people can't. That's why it was used to monitor power lines, especially up in the mountains here in Colorado. Quadcopters can get to places where it would take a service technician a lot longer to get there, and then it would be very tedious for them to go up and constantly check each one, whereas quadcopter with different sensors can quickly do a flyby and then send back data, and then if they're in problems, go out and fix it.
And there's also a lot of practical applications for search and rescue. Like if there's a big accident, you could send out teams or kind of fleets of drones to survey the area, look for people, and send it into hazardous environments that people couldn't go into.
Cool. Well, that's good news.
Now, so with the sensor, right, it only tether it to a location, or like when it starts reaching towards an object like a wall, will it like slow down and stop itself?
Oh, yeah, that gets back into the idea of the TID loop. I mean, so the fact that we can monitor not only how far, like the distance of the wall, we're also monitoring how that's changing over time. So essentially how it's basically the velocity of its error. And so if the velocity of its error is decreasing, then we actually don't have to, let's say if you're accelerating towards the wall, then you actually don't have to accelerate as fast. Right? So the wall's only approaching. Whatever action you did previously is going to use the wall just fine. Next question.